Welcome to our third lesson on sound. How are you all doing, Devi and Joy?
I'm happy.
I'm excited.
That's so good to hear. At the end of the last class, I had mentioned that in the next class we will look at transverse waves and then some more definitions. Let's start. To recapitulate quickly, longitudinal waves are those waves in which the particles of the medium vibrate back and forth along the direction of progress of the wave. Now, let us move to transverse waves. Here's a graphical representation of a transverse wave. This is the kind of wave you see on the surface of water or the wave formed by a fluttering flag. As you can see, in this type of wave, the motion of the particles of the medium is perpendicular to the direction of propagation of the wave. It's like a T, capital T. So it should be easy to remember. Now, let us have a look at some of the basic definitions with respect to a wave. In this visual, you can see both the types of waves. Let me mark for you the distance that is called wavelength of a wave. As you can see, the wavelength is simply the length of a wave. It is the distance from crest to crest, or from trough to trough of a transverse wave. So, wavelength is the distance between successive crests or successive troughs of a transverse wave. Now, coming to a longitudinal wave, wavelength is the distance between the midpoint of a compression to the midpoint of the next compression. Or, wavelength is the distance between midpoint of a rarefaction to the midpoint of the next rarefaction. So, wavelength in the case of a longitudinal wave is the distance between the midpoints of two successive compressions or the distance between the midpoints of two successive rarefactions. That is simple, isn't it? That's the length of a wave. All you need to remember is from where to where is the length of a wave. Clear?
Yes, that is simple. But you had mentioned amplitude in one of the pictures. What is amplitude?
Good question, Joy. I was waiting for one of you to ask this question. Amplitude is the maximum displacement of the particles of the medium from the mean position. In this figure, you can see the amplitude marked. In this figure, you can see that the red wave has a higher amplitude than the green wave. So, greater the maximum displacement, greater is the amplitude.
Okay, I get that. That is pretty straightforward. Is there any other definition for today?
Just two more definitions. Look at this picture. In both the diagrams, the x-axis measures time. Now, if you count the number of complete waves in the upper diagram, you will see there are 14 of them completed in 10.5 seconds. Whereas, in the lower diagram, there are 10 waves completed in the same time of 10.5 seconds. So, here's the new idea. How many waves are completed per second? Then, in the upper diagram, the number of waves completed per second is 14 waves divided by 10.5 seconds, that is 1.33 waves per second. And in the lower diagram, the number of waves completed per second is 10 divided by 10.5. That is 0.95 waves per second. So, here's the definition. The number of waves completed per second is said to be the frequency of the wave, and it is measured in hertz. So, the upper wave has a frequency of 1.33 hertz, and the lower one has a frequency of 0.95 hertz. And here is the last definition for today. The time taken to complete one wave is the time period of the wave. Thus, the upper wave has a time period of 0.75 seconds, and the lower wave has a time period of 1.05 seconds. That's all for today then. Hope you all have understood the definitions. As the lesson progresses, we will be using these terms very often, and so you must become familiar with their meaning and definition.
Thank you, sir.
Thank you, children.